So we got 4 of them that are coming due on Monday, so let's have a look. So we got any questions on this one here? This is a 2D moment problem. The general approach on these things is to break the angled forces up into components and then multiply them by their moment arm. Okay. So if you want to sum moments about A, this is 191. All right, so I'd probably go, cosine of 55. So what's happening there is you've got a right triangle that you can make. And so if you go cosine 55, that's the adjacent angle. So that's right there, times the 820 newtons. And then what that is, that's an X force. So you would combine it with a Y moment arm. Okay, so what I do out of habit on these, I just write down the numbers first, then I look at it, and if I have a piece of paper there on the table, and I hold the bottom right corner down here, and I push the upper left corner to the right, the paper will rotate that away. That's clockwise, so that gets a negative. Okay, and I think you're going to have another thing to include in there to get the total moment, which you'll have to put in there too, and you'll get the, I think it's negative 177 if I'm not mistaken. I think. Okay. So we good on that? You gotta put that other term in there.
Wait, is this homework?
Yes, it is. Yeah.
Is this week?
Due Monday.
Okay.
So it's 191, 192, 193, and 201. All right, we're good with that? Okay. All right, and that's the basic approach on these things. Here you're going to have, you're going to break these things up into components. So they'll look something like that. Okay. So you just do the trig and multiply by the moment arms is the thing on this. You could sum moments about A again. And for instance, you'll have cosine 50 times 1900, right? No, times 1900 newtons, and then that's got a moment arm of 0.7 meters. Okay. So that's an X force. Those are the Y moment arm. Okay, so that's one way to remember to get them oriented properly is that you look at the relationship between the force and the moment arm. They should be different. If one's X, the other should be Y. Okay. And then you're going to have some other terms to put in there. One of them is going to zero out, so there's one of those that you're not going to have to work with. You know, it'll just zero out. Okay, I'll mention that. So we're doing all right with that. You got some others to add up. You just get the total moment about A. 154, I think, is what it is. Positive, I think. So after you add everything up, you'll get sum of MA is 154 Newton meters. I think it comes out to be positive. Any questions on that one? Yeah. Now the next one's a little bit trickier yet. It's like that. Now, what you can do on that is you can find moment arms to each of those forces and then break the forces into X's and Y's and break the moment arms into X's and Y's and combine them together. But there's a sneakier way to do this that'll save you a little bit of effort if you want to use it. And what you can do is set up your own axis system. You know, we generally use X horizontal, Y vertical, but you don't have to. You can set up your own axis system if you want. And then if you were to do that, what you would have for a sum of moment about A would be, see what you can do now is you can take the component on that axis system, so that would be that comes from right here on that triangle, okay? So what that is, that's opposite the angle, so that would be sine of 61, wouldn't it? Times the 420, and that's newtons, of course. Okay, that will get you that component of force, and then you're going to want the distance from A, and that'll be 0.4 meters. And what that's going to come around, if you held your pencil on the table like that and pushed on it in the direction of the purple arrow, that would go clockwise, I think, so that would get a negative. Okay. And then you're going to have another one there to put in. I would just use the same approach on this. You could just use standard X horizontal, Y vertical on this if you wanted to. It would just get a little bit more involved. So I would tend to do it this way because it's quicker and more direct. That's a little trick you can use in statics. It comes up a few times. We'll touch on that a few times as we work through stuff. We good with that? We got any questions on what I'm up to there? One thing I would caution you on is the moment arm out here. If you want the moment arm there, remember it's not 0.4 because you're taking the moments about A. So that moment arm would come all the way from A to that point. I've seen people make that error before where they'll take the distance that's listed, but you want to calculate the distance to A from that point, which is a very simple calculation, but all the same, you got to remember to measure consistently from one point to where you're taking moments about. In this case, it's point A. Okay. Questions on that?
Would that be a negative cosine for your x since it's going to the left?
I'm sorry now. Okay.
Cosine for that cable 700 newtons?
All right. Now, the question there is, would you use a negative for the cable force when you plug it in because it's going to the left? I don't do it that way. There is a relationship between force and moment sign conventions, but it is not in any way a direct, easily described relationship. So what I do when I'm doing moments is I write the numbers down, then I look at how it would rotate, and that's what I put in for the sign. Okay, I don't try and combine force moment arms or sign conventions, which would be the force to the left, with a moment sign convention. They don't relate directly.
You just do the cosine of that 9 and then the cable and the distance, and
then look at it and go,
say, is it rotating left or right?
Yes,
rotating left,
right. And don't try to embed signs. It can cause problems, so I don't embed force sign conventions on that. Okay, so just look at how that rod would rotate. Just put the numbers in here. You're going to have a trig function in there. You're going to have the force here, moment arm there. Just put those in as numbers. And after you've done it, then you put the sign. That's how I do it.
Are those multiplied, or those are that plus that?
I'm sorry now?
It's like that plus that.
Yes, it's just sum of the two, yes. And now, of course, it might be the difference if it's a negative. I mean, whatever, but you're just adding the two things together independently. Yeah.
Okay.
Right. Other questions on that? All right. Good. All right, the last one is 3D. Okay, and this is what we were touching on Friday. So this is a 3D one, so I tend to use a more formal approach on this. All right, so this is a 3D vector problem. So the deal on this is you want to find a force vector and find a position vector that goes from the point to the force and then cross them, R crossed with F. All right, so that's how you would figure this one out. So you're going to get the moment about A on this is equal to R, and I used AC, and you cross it with the force vector that goes from C to D. Okay. So you start with that. Now that formula is on your formula sheet. It's down in the lower left. And I would suggest that you start looking at the formula sheet a little bit, because that's what I'll give you on the test. This will be your notes for the test. So just look at it, know where the stuff is. So you've got M equals R cross F on there. All right, so what you're going to do then on this is find FCD, okay, and then find RAC, and then do the cross. That's the steps. All right. So what you're doing when you find FCD is you're finding this force as a vector. Then you're going to find the vector that goes from A to C. So this RAC has to be from the point to the force vector. So the way I think about that is I think about that like a wrench. You attach the wrench to the bolt, you extend it out to your hand where you exert the force. Okay, that's how I think about that position vector. Starts at the point you're going to take moments about, it extends out to wherever the force is applied. Then you do a cross. Okay, now the cross, keep in mind that the formula for the cross is in the lower left-hand corner of the formula sheet. You just got to plug this stuff in. Okay? So, that's all there is to it. You just plug in that formula. You'll get a 3D moment out if you plug in the position vector and the force vector. Okay? So that's the steps, so to speak. Now, you need to find a force vector, which, again, we've done lots of times now, so that is something, you should be familiar with. And so, step the first there is to find the coordinates of the points you need to deal with, which are A, C, and D. Okay. So I just went ahead and found those Cartesian coordinates. So what do we got? We got 1.6 for X. 0.5 and 1.2 makes negative 1.7 for Y, 2.4 for Z. 0 in the X, negative 1.2 in the Y, 0.4 for Z to get to C. And then what do we got? Negative 1.2, 0.6, and 1.7 to get to A. Now I'm sure you'll do something like that again on the test and all that, because it's something you're supposed to know. Now remember, when you're doing this, write that stuff down, so that when you start doing vector operations, if you bust a number, it's not uncommon to put a negative in there when you don't want or something like that. If you write it down and I see where that stuff comes from, it's not, I'll take a point off or something. But if I can't tell where something came from, that's a little different deal when I start grading something, all right? So it's on you to show me how you did things. Now, don't overkill it, but show the work, okay, how you're getting to where you get, because it's in your interest to do that, all right? We good with that? All right, so now we've got the coordinates on the points. Now you find the force vector, and we've done this many times now. So to find FCD, you take RD minus RC, you get RC to D. Take the square root of sum of the squares, you get the length in meters. Divide through by the length in meters, you get a unit vector. Scale the unit vector up by the magnitude of the force, and you get a force vector. So that's the steps, okay? So RCD is RD minus RC. You got to remember to turn the letters around. Square root of sum of the squares gets you the length. Divide through by the length, you get the unit vector. Scale it up by the force to get the force vector. So really what you're doing, you're taking that position vector from C to D, you're taking the length of it out in meters, because you don't care how long it is. You just care what direction it points. So you take the length in meters out, and then you scale it up by the force to turn it into a force vector that points the proper direction. That's what you're doing there and why you're doing it. Okay. Okay. So there's a force vector. Now, after that, what you want to do is find a position vector. The position vector is like the wrench. It starts at the point that you're taking moments about, which is A, and then it goes to C. So this is RAC, the vector that goes from the point about which you're taking moments to the force. So it's like a wrench. It goes on the nut where you're going to take moments about. It extends out to your hand where you exert the force. Okay? Now that's just a position vector. You leave that as is. You do not want to unitize that, okay? Leave it as it is because the length of that vector affects the moment, right? The longer the wrench, the bigger the moment. So I know quite often we're used to unitizing those vectors, but in this case you don't because you want to leave the length in there, okay? So we want to do that. So now we get a position vector. And what you then do is you do a cross product. And yeah, you start with R and you cross with F. So a couple of things on that. So then you do the cross product, okay? We good? We got that stuff? Okay, we're good. And you do a cross, and there's the formula right there. And, you know, there's lots of ways to do crosses, and I don't care how you do it. Whatever way you like is fine with me. You know, I think the people that do it the LBCC way it's taught here kind of do this, right? They
figure it out and remember the trick.
Yeah.
You just draw you just take your matrix,
and
then you draw your matrix right next to it.
Okay.
And it's like over 4 over 4 over 4. No crossing at all.
Oh, really?
It makes this funny. It's a cross product and you're not crossing.
Oh. Okay. The stuff I've seen people go like that. 1, 2, 3, and then they go the other way. That's what I see. I'm not quite sure. I have to look at it to see what exactly they're doing, but that's kind of what they're up to. Then they go back the other way. So this way is kind of a cross. I mean, there's lots of ways to do it. And like I say, I don't really care how you do it. It don't matter to me. You have the formula right there if you need it. Okay, I'm screwing up. No, I'm doing. What am I doing? I'm having problems here. Yeah, I'm definitely having some problems here. There we go. That's better. All right. Like that. You can do it like that too. I mean, again, okay. The way I learned was to take out the top row, first column, cross what's left. Take out the top row, middle column, cross what's left. Take out the top row, far right column, and cross what's left. However you do it, again, it doesn't matter. I give you the formula for it, okay? Formula's right there. You just plug the numbers in. Now, the one thing to remember on this is there's a negative sign on the J. It's plus, minus, plus, okay? The other thing, okay, and now once you get that is a vector. It has an I, a J, and a K component. So we're going 1.8 times 1380. That's for the X. So 1.8 times 1380 minus negative 1.3 times negative 345. That's the I component. And then we're going 1.2 times 1380 because we've crossed out that middle column, minus a negative 1.3 times 1104. That's the J. That gets the negative on it. And then the last one there is 1.2 times negative 345 minus 1.8 times 1104. That's the K. That is a vector. It has I, J, and K components. If you want the magnitude, you take the square root of sum of the squares. 45, 42 Newton meters. Okay. So we good with that? Okay. Now, two important points on this. One is it's R cross F. That's the formula. Remember to do it in the proper order. R crossed with F. So R first, F second. The other thing is the vector goes from the point to the force, AC. If you make an error on either of those, you'll get sign errors. You'll just have the negative of what you're supposed to get. If you do 2 errors, you'll get 2 sign errors, you'll get the proper numeric answer, but you aren't doing it correctly, so that won't be right, okay? So just remember to get this stuff right. Right order, right signs, all that stuff, okay? We all right with that? Questions? No? Okay. All right, so that's the homework that's due Monday. Okay. Okay, now let's go back to what we were doing, because we were actually doing this stuff before. So let's have a look at it. So why don't you get that position vector? We did this 3D moment. We did it visually, which is a little bit of a chore, and I don't recommend doing that. I just did it once to show you kind of what this stuff means. The cross product just automatically generates this stuff for us. Okay, so on page 310 on the right. So why don't we run through this one here, and remember the position vector goes from the point to the force. Let's go from A, which is the point, we're on page 310, to the force, which is B. So we'll go from A to B. We already went from A to C to try that. That was the easiest one because it's the simplest position vector. But you can go to any position vector you want, or any point on the force vector. I'm sorry, I should say it that way. Any point on the force vector. So let's go to B. Let's go from A to B this time and run the cross and see what we come up with. So why don't you just take a couple minutes and do that. So get the vector from A to B first, and then run the cross, okay? I'm on page 310 on the right-hand side. And I've got that kind of set up for you to do, a good bit of it anyway. Okay. Yeah, force vector is the same, yeah, on the left. Force vector is just a force vector. The position vector is what could change. But the thing that will happen here on page 310 is that we'll get the same answer. We'll generate it differently by combining different numbers, but the answer will be the same. That's the truth. So I'm sure this will be on the midterm because it's an important concept. So just get this one figured out. Force vector, position vector from the point to the force to the cross, R cross F. So it's a series of steps. You just want to get those figured out. Okay, the position vector ought to be 0.7 and negative 0.2 when you're on the cross. See, when I'm doing those position vectors, if you have a choice, the more zeros you can get in the position vector, the easier the cross is, of course. So that's why I like to use that other one, A to C, because it's just got 2 zeros in it and one one number. It's just negative, whatever it was, negative 0.400, I think. So this one has 1 0 in it, so that's not all bad. So now you just do the cross. So we got 0.7, negative 0.2 for our AB, and then just run the cross product. Now, another thing you'll see on this, so there might be a little bit of rounding error in there when you do the cross. So you may not get exactly 0 for one of those.
0.7 times 144, I think is 0 exactly.
0.7.
I did 0.7, times 144 minus 0.2.
There we go. So it should come out pretty close to 0. So what you're seeing there is some rounding error with this all. It's not a big issue. Y'all getting to that okay? Working out? So that's the basic drill on doing moments there. Okay. So that's just a process that you want to, again, figure out and be able to work through. Okay, so we're good on the slide there? Ready to, we good? Done with that? Anybody still copying that? Are we doing all right? Okay. So again, you got that formula in the lower left-hand corner of the formula sheet if you need it. Okay, it's right there. So what we've just found there is just the moment of that force about A. Now, this, and so, as I think I had a picture of this drawn up where I showed the moment vector and then showed how that was normal to the rotation that would occur. Okay, so another way to visualize this is that force vector is like a rocket or something. You have a rope tied to the rocket and it'll just swing around that point. The moment vector then is normal to that plane in which that force would rotate. It's a little difficult to draw it, but there's about the best I could do with it, okay? So the orange MA is how that force would rotate about A. The moment vector there is normal to that plane that it rotates in. So think of the moment as being a wheel, the moment vector is an axle about which the wheel rotates. The direction shown by the right-hand rule. Okay? So one way I've described that is it's a free moment. It can go any way it wants, and if that moment can go any way it wants, that's what it would do, and that vector would describe it. That would be the axle.
So if you push it at the corner there, it would do a 0 in the X, 557.6 in the I, Y, and whatever in the J.
If that would be the moment vector, so that would describe the direction of that axle. About which it rotates.
How many Newton meters per second?
On each one of those axes, yeah. Then you combine it proportionally, you'll get that direction that I'm trying to draw. I mean, that's what that is. Okay.
I'm surprised that it doesn't wake up.
Okay. Now there is another aspect of these 3D moments because I don't know, there isn't really a term I've ever heard for this, but I made one up. I just call it a free moment. It can go anywhere it wants, okay? Now, a lot of times, though, it can't go anywhere it wants. You're going to force a moment to occur about a given axis. So that's the last little bit we'll do with moments, okay? So this will be a 3D moment about an axis, okay? So there's a prop on a hood of a car, okay? And so what's happening there is we've got a force that's going like that. That's going to create a moment about this hinge that does something like that, okay? But there's two hinges, right? One there and one there. So what's going to happen here is that you're forcing that rotation to occur about a given line. It's not just occurring anywhere it wants. So that moment vector, what I call a free moment vector, is reacting to just the direction of the force in this one point. Let's call it A. But the physical situation we've set up here is with two hinges. We're going to make that moment rotate about this line right here. Okay, remember, the moment vector describes the axle about which the rotation would occur. So if that force from that prop would rotate any way it wants, it would rotate about this axle in yellow, this one here. But because we put a hinge line in there, it can't rotate about any line it wants. It has to rotate about that line between the hinges. So what we got to do is project it down. If we want to find the actual moment about that hinge line, we have to project it down onto that line there, okay? Okay, if that arm there, if that bucket is going to pick up that big chunk of concrete and accelerate it, that'll be a dynamic moment, okay, is what that'll be. You know, if and when you take dynamics, you'll learn about that. That force might be something like that. It might rotate something like that. But if I'm in that cab there, my biggest concern isn't that free moment. My biggest concern is the moment about this track right here, because I don't want to flip over like that when I jerk that piece of concrete, okay? So again, I'd look at that free moment, but then I would project it onto the line is what I would do, all right? So, and again, it's just tough to draw this stuff on a flat piece of paper, but the free moment's kind of up like that. That's the axle for the free moment, but I would be more concerned about that moment there, okay? About that axis. So what you do to find this number of a 3D moment about a given axis is you project it, and a projection is done with a dot product. So what you do is you find the moment vector, call that m sub a, and then you project it down onto the given axis that you're interested in, and that would get you what I would refer to as MA, let's call that B over here, MAB. That's what I might want to know. And it's a projection. You're projecting the moment vector onto a given line about which you're forcing the rotation to occur about. So you're doing a dot product to finish that up. So you do the regular m sub a calculation, and then after you've done that, then you do one last step as a projection. All right. So we're on page 320 now. So we're going to do this moment one more time. One more time, okay? So I guess we're doing this thing an awful lot, so this is the last run we'll give it. So what we're going to do here, instead of a block now that I've had before, I've got the outlines of a block that I'm using for dimensions. Then I'm going to have an axis that runs from A to point D there, over on the far corner. And I want to find the moment of the 600 Newton force about that axis AD. I've got a couple bearings there, let's say, that are holding that axle, and I want to know how much moment am I going to get about this axle? What's going to make that plate spin about those two bearings at A and B? That's the physical question I'm asking here. All right. So the steps to accomplish this start off exactly the same as what we've been doing so far. So once again, we find FBC, and I think we've done it twice now, so I think we pretty well have done that enough. So we know FBC, and that's the exact same process that we used before to find it. So it's negative 289, negative 506, and 144 newtons. All right, so once we've got that, what we want to do is find the moment about some point on the axle there from A to B. So we've already done it about A, so let's just use that. So once again, I do a cross product. I'm using the position vector from A to C, which is on that force. So that's negative 0.400. I do the cross, and I come up with the moment we just came up with. 0I plus 57.8J plus 202.3K. That's the moment about A caused by that force. Okay. So now what I want to do is take that moment vector and project it down onto that axle that I'm going to force that moment to occur about. All right. So there's a picture of what I'm going to do. I'm going to take that green M sub A, which is normal to the plane in which that moment would occur. So if that moment was just free to spin, it's going to do something like that. So what I'm going to do is start with that M sub A vector, which goes up like that. So there's MA, and I'm going to project it down onto that axle that goes from A to D, because I'm going to force the moment to occur about that axle. So
we're doing something like orthogonal to AB and BC.
Orthogonal to AB and BC.
Is that what we're doing? We're dotting them. We're doing like something that's going perpendicular to the two vectors.
I don't know if we are. I can't juggle that in my mind quick enough to get you a good answer. What we're doing here is we're just taking that vector and we're projecting it down onto AD. So I don't know if we have all these right angles going on or not. We're kind of taking a right triangle there and finding the cosine component of it on the bottom is what we're doing. I mean, so I don't know if we're orthogonal. I don't think we've got like 3 orthogonal things going here. I don't think, because the axle's somewhat arbitrary where we put it. Okay. So what we're going to do is just take that free moment vector, MA, and project it down onto the axis. We're going to force the thing to rotate, which goes from A to D. Okay. So what we want to do then is find a vector from A to D. So we'll go RD minus RA. We'll get that RAD, negative 0.70. That's how we get from A to D. We're doing a dot product, so we want a unit vector from A to D. So we find its length. We take the square root of sum of the squares. We get 0.806. We divide that through, and we get the unit vector from A to D. And then we dot it with our moment vector, and we get 50.2 newtons. So what I'm doing for that dot product is I'm taking the moment vector, the 0, 57.8, 202.3, and I'm dotting it with the unit vector that goes from A to D, negative 0.496, 0.868, and 0. So to do the dot, I multiply the like components together. So 0 times negative 0.496, 57.8 times 0.868, and 202.3 times 0. And what I get is 50.2 Newton meters. So when that force contacts this little plate down here, it's going to cause a moment around that axis that has a magnitude of 50.2 Newton meters. Okay. Like that. If I want to convert that into a vector, I can take the magnitude, the 50.2, and multiply it by the unit vector from A to D. All right. So if we want a moment about an axis, we have an extra step. We take the moment vector about some point on the axis and dot that with the unit vector for the axis. And that will get us a magnitude of a moment. Okay. And then if I want to make that into a vector, I then multiply that through the unit vector for the axis. So are we doing all right with that?
Yeah.
Okay. Now, when you're doing these, that page 320 that we just went through, that that's a good model, 310 and 320. are good kind of charts on this for going through these, all right? And think about it in that way. It's just a series of steps that you want to do to get to the answer. Okay. So why don't we do a couple of these for Wednesday? How about 202? So for 202, we want to do it twice. We want to go from A to B and A to C. Okay, so the first time you use RAB and the second time you use RAC. And then let's do 211. You can use your answer from 201, which you're doing for Monday. So you can go ahead and use that. And what you're going to do there on 2011 is just take the moment vector from 201 and then find the moment about an axis with it. Okay? So you don't have to do the moment about A all over again when you do 211. You can just use the answer, which I think I put right in the problem statement if I'm not mistaken. Yeah, I did. And so you can just use that moment vector and use it to find the moment about the axis that goes from A to, what is that? A to B. Okay. So 202, you got to do that one twice using two different position vectors. 211, you can use your answer from 201. Okay, we'll figure this all out on Monday, but we're looking at a test a week after next. Okay, so that'll be week 5. Okay. All right, here we go.